Okay, so I got a request here for section 4.3, practice question 6. Let's get started. A fully dressed astronaut weighing 1.2 times 10 to the 3 newtons on Earth. So you got this astronaut, and when the astronaut is on Earth, he or she has a certain weight, and they are giving you the magnitude of this weight, which is also the magnitude of the force of gravity. So you need, this is very important, and they're telling us it's 1.2 times 10 to the 3 newtons. So this is an important part of the given, because you need to remember that the equation for the force of gravity is this, and when we're using magnitude signs, we can put magnitude all around it, and if we divide both sides by m, we get that the force of gravity divided by the gravitational field strength near the surface of the Earth will allow us to calculate the mass. And the mass will be constant anywhere. So that's 1.2. This is all scalar now because we got magnitude signs that eliminated the direction. So you won't see any plus or minus signs here, just the scalar parts. And this is going to allow us to calculate the mass. So this is really important for us here. So we can find the mass of this astronaut, and that is going to be the mass of the astronaut anywhere, okay? Anywhere. And this fully dressed astronaut with this weight on Earth is about to jump down from a space capsule, okay? And the space capsule has just landed safely on planet X. So let's draw the surface of planet X here. There's the surface of planet X. Here is the space capsule. Okay, maybe it looks something like this, right? Kind of looks like something out of Star Wars, but that's okay. And here is the astronaut. And they're about to jump from here on planet X, and they're dropping to the surface, which is 2.8 meters below. So what they're telling you is that they're going to drop, they're going to fall by 2.8 meters, okay? And we're going to assume that their initial speed here is 0, that they're just kind of step off the ledge and fall. And we also know that the astronaut's gravitational potential energy relative to the surface is 1.1 times 10 to the 3 joules. So what they're telling us here is that when the astronaut is right here, the astronaut has a gravitational potential energy because they're on planet X, and it's equal to 1.1 times 10 to the 3 joules. And they're saying it's relative to the surface. So what they're telling us is this is what we're considering to be height 0, the ground right there. At this level here, there's no gravitational potential energy from the gravitational field of planet X. But we know when the astronaut, I guess I should give the astronaut some arms, that when the astronaut is here, he or she has this known gravitational potential energy. So that's what we know so far. So that's our G. Okay, so we've written down our G. What's up, G? Next, required for part A. And it says, what is the magnitude of the gravitational field strength on planet X? So they want to find G for planet X. I know on Earth, I get it. On Earth, we got the 9.8 newtons per kilogram. I get it. But we're on a different planet. So we need to find G for this planet. Well, analysis. Well, we're in the energy section, and we're talking about gravitational field strength, and we've been given a gravitational potential energy. So that all leads us to this equation right here, which is slight variation from the regular one. So I just can't put G, I have to put GX because it's the gravitational potential energy on this other planet. So what we're now going to do is we're going to divide each side by M and H. We're going to divide each side by M and H. And that'll leave us with this equation right here. So I've done the dividing of each side, and now I can substitute in some numbers, right? Now I can substitute in some numbers. Let me give you a little bit more space here. Here we go. So the gravitational potential energy, when it's on this planet and the astronaut here, he is on that little ledge there, 1.1 times 10 to the 3 joules, right? In the bottom, the mass, oh, the mass doesn't change. It doesn't matter what planet you're on, right? And the height, well, it's 2.8 meters. And that will allow me to calculate the gravitational field strength on planet X, the magnitude at least, right? Well, the direction wouldn't be some grand mystery. It's down towards the surface of the Earth. Gravitational fields always go down towards the surface. And finally, we have a solution, and it's going to be about 3.2 newtons per kilogram is the gravitational field strength right there. And just like on the Earth, if that's the gravitational field strength, it also means, going back to something we looked at a while ago, that if you were interested in finding the acceleration due to gravity on this planet, it would be negative 3.2 meters per second squared. You may remember, or may not, in class a while ago, I said that these were mathematically equivalent, newtons per kilogram and meters per second squared. So there we have it. We have calculated the gravitational field strength on planet X. Okay, so now we're going to move on to B. There's a part, whoa, what happened there? There's a part B to this. And they want us to find out in part B has its own required. How long does the jump take? How much time does the jump take? Well, we know that this object, this person, this astronaut is going to fall downward towards the surface of the Earth by negative 2.8 meters because down is negative, okay? And we do know that there will be an acceleration for this astronaut, which is negative 3.2 meters per second squared. We talked about that in solving for part A. And we're going to assume that the astronaut here, he just kind of steps off. So its initial velocity is 0 meters per second. So this is basically my G, my given. What's up, G? So now, this is a good time for us to review our kinematics stuff, all of our wonderful kinematics equations, and we need to pick an appropriate kinematics equation that will allow us, oopsie, let me fix that, that will allow us to calculate time, and it's this equation right here. Now, since this term here, initial velocity is 0, that whole term disappears, and we're left with half times the acceleration delta t squared. We're going to multiply both sides by 2, which will lead us to this. We're going to divide each side by the acceleration on this wonderful planet X, which would be probably a lot of fun to go visit. And that's going to be our time squared. So now we can go to substitute. Time squared is equal to 2 times the displacement at negative 2.8 meters, all divided by the acceleration of negative 3.2 meters per second squared, right? And we're going to get our handy dandy fancy dancy calculator out and solve for this. So we put that in our calculator and we get delta t squared is equal to 1.275 seconds squared. We have to find the square root of this, right? Because that's time squared. So I'm just looking at my calculator here, and I want to find the square root of 1.75, what I just did there, and it's 1.3. So here's my solution. Time is 1.3 seconds. So we've done that using kinematics, stuff we learned a while ago. So this is a good chance for us to review all that wonderful stuff. So now, kids, we're on part C. What is the astronaut's maximum speed? So once again, this is another question. Notice how the capsule's color changes all the time. Oh, now the astronaut is blue. Maybe they're running out of oxygen. You never know. So here's our given. We found a whole bunch of information from part A and part B. And we all know from our experience on Earth that the maximum speed will occur when we find the final velocity just as it hits the ground. Hitting the ground does not mean you hit it at zero. If things hit the ground at a velocity of zero, nothing would break. Okay, so they hit the ground with a certain velocity. That's what we want to find. And we know the displacement is negative 2.8 meters downward, right? We know the acceleration is negative 3.2 meters per second squared. We know that they start with a velocity equal to 0 meters per second, and we want to find this final velocity. So we can use some analysis here. And here's a really good equation to use for analysis, because we know initial velocity, we know acceleration, we know time, we can solve for final velocity. So I'm going to multiply both sides by time. Multiplying both sides by time will give me this. Now I'm going to bring this initial velocity over to the other side, and when I bring it over to the other side, it becomes positive. And the other term here was positive already. It wasn't written, but it's positive. There's no negative sign in front. It's positive with an equation with algebra. And now we are going to plug in the values here. So we're going to substitute. It started at 0. The acceleration is negative 3.2 meters per second. And it fell, we just figured that out in the previous question, for 1.3 seconds. And that'll give me my final velocity. So I get my handy dandy fancy dancy calculator out, and I take 3.2 and I multiply it by 1.3, 3.2, and I multiply it by 1.3, and we get a final velocity. Remember, there's a negative sign there. Don't forget that negative sign, negative 4.2 meters per second is the final velocity. And bingo, bango, we are done. Oh, okay. All right. Thanks for asking this question. Greatly appreciate it.